Next we turn to another fundamental concept in the theory of rigid bodies, and it's the moment of inertia. The moment of inertia is defined as follows. Let us once again start from a rigid body. This here denotes the inertial frame. Then somewhere here we have our body fixed frame, and let's say the body fixed frame rotates with respect to the inertial frame with some angular velocity vector omega. Let's now pick a point, one of the mass points of which the rigid body consists. So let's say we pick the nth, so the Greek letter nu, mass point number nu, and the position vector of this mass point is r prime, because we look at the position vector relative to the body fixed frame. So r prime with the index nu. Yeah, so this is the position vector in the body fixed frame of mass point number nu. And let's now look at the angular momentum of our rigid body with respect to the origin of the body fixed frame and as viewed in the inertial frame. So when you define the angular momentum is always defined with respect to some reference point. In this case, we choose the reference point to be the origin of the body fixed frame. But then in the definition of the angular momentum, there are velocities, and for the velocities, we take the velocities as seen, as viewed in the inertial frame. So what is that mathematically? We have to, if we look at the total angular momentum of the entire rigid body, we have to add up the individual angular momenta of the n mass points that make up the rigid body. So we have to sum over all nu, going from 1 to n. Now the angular momentum of the mass point nu is given by its mass, m nu, then its position vector relative to the reference point, and we chose as the reference point the origin of the body fixed frame, so that position vector is r nu prime. And then the vector product with the velocity as seen in the inertial frame. And the velocity seen in the inertial frame, that is r nu prime dot. Again, it's the velocity relative to the reference point. So it's not r nu dot, but it's r nu prime dot. So it's the velocity relative to the reference point. For this we know this is equal to the angular velocity vector product with r nu prime. So in total, the angular momentum has this form. It's m nu r nu prime vector product with omega vector product r nu prime. Now what you have on the right hand side, that is a linear operation acting on omega. So if, for example, you say omega is omega 1 plus omega 2, then since the vector product is linear in both arguments, you can split this into two terms of the same structure, one with omega 1 and one with omega 2. So it's a linear operation. It's a linear map acting on omega. And this linear operator acting on omega, let me denote that by a capital theta. This is a linear operator acting on omega. And this linear operator is called the moment of inertia. This is now defined as an abstract operator. Now we should look at its components in a specific frame. And in particular, let's look at its components in the body-fixed frame. When we have a linear map, a linear operator, and we want to calculate its components in a specific frame, then the components will form a matrix, and the elements of the matrix are given by scalar product EI prime, because we are working in the body-fixed frame, with linear operator, moment of inertia, acting on EJ prime. This is so we have an abstract linear operator, and we apply it to a basis vector, and then take the scalar product with some other basis vector, the same basis, and in this way we get the component. We get a matrix element of the in that particular frame. Let's insert the expression for the moment of inertia that we had found on the previous page. We obtain a sum over all nu from 1 to n. We have the mass m nu, EI prime, scalar product. Now, the moment of inertia acting on the basis vector gives r nu prime vector product with EJ prime vector product with r nu prime. So if you here on that page you compare the last line with the line before, you see the definition of the moment of inertia. Here it's the moment of inertia acting on omega. Now it's acting on a basis vector. So in the formula before the last line, you have to replace the omega by the basis vector, and you get the result that is written here in the square bracket. That's moment of inertia acting on basis vector EJ prime. In the body-fixed frame, the position vector r nu prime can be written as a linear combination of the basis vectors of the body-fixed frame. This can be written as sum over k, then the component of the position vector, the kth component of the position vector in the body-fixed frame, times the basis vector ek prime. And we can do the same here for this position vector r nu prime. Yeah? So in both cases we can write this as a linear combination of the basis vectors. When we do that, then we have the sum over nu, m nu, sum over kl, x nu k prime. So I take the components in front, the x nu k primed, and the other vector we can take as a summation index, we can take L. So then we have x prime nu L. And we have EI primed, as before. And then we have a basis vector EK prime, vector product with EJ prime, vector product with EL prime. That's a good occasion to look more closely at this bracket here. You have a double vector product. There's a nice formula for the double vector product which you may have seen already. The general formula reads A vector product with B vector product C. The formula for that is A scalar product with C times B minus A scalar product B times C. You can use that to say inside this bracket we have EK prime scalar product with EL prime times EJ prime minus scalar product EK primed with EJ prime times EL prime. Now this is, we assume that this is an orthonormal basis. So this is a Kronecker delta, KL, and this is a Kronecker delta, KJ. So it's 1 if the indices are equal, and it's 0 if they are different. Now the whole square bracket is multiplied as a scalar product with the EI primed in front. So now we incorporate the EI primed. If we do that term by term, in the first term we get a scalar product EI primed with EJ primed, and this gives another Kronecker delta. So we have then delta KL, delta IJ. And for the second term, we get a scalar product EI primed with EL primed. It gives another Kronecker delta. So this is delta KJ, delta IL. What does that do with our expression for the moment of inertia? We still have the sum over all nu, m nu, that doesn't change. And then we have the sum over KL, then we have these two components, x prime nu k and x prime nu l, and then we have this combination of Kronecker deltas. What happens in the first case, with the first pair of Kronecker deltas? Well, first of all, the sum over L collapses, and we can drop the first Kronecker delta, the delta KL, and we are left with the sum over K. And then we have x prime nu k, x prime nu k, but the sum x prime nu k, x prime nu k over all k. This is nothing but the length of the position vector squared. So the first pair of Kronecker deltas simply gives the length of the position vector squared, and there's one Kronecker delta that remains, it's the delta ij. Then let's look at the second product of Kronecker deltas. In that case, both the sum over k and the sum over L collapse. We can drop both Kronecker deltas, and we are left with the product of components, where in the first case the k is replaced by j, and in the second case the L is replaced by I. So I'd like to write it in this order: x prime nu I, x prime nu j. So this is finally an expression for the components of the moment of inertia in the body fixed frame. In the body fixed frame, the the distance of mass point nu from the origin of the body fixed frame is always the same. It's fixed. So this is constant in time. And in fact, all components of the position vector are constant in time, because with respect to the body fixed frame, of course, the point nu doesn't move. So the components x prime nu I of the position vector, they are constant in time. So this matrix element, this component, is time independent, like all the x prime nu i's. I'd like to talk a bit about some basic properties of the moment of inertia. A first property, when you look at our result for the components of the moment of inertia, you see that the matrix is symmetric. Because look at the last line inside the square bracket. The first contribution is proportional to a chronica delta, delta ij. That's obviously symmetric in I and j. And the second is a product of the ith and the jth component, and that's also symmetric. So a first basic property of the moment of inertia is that it is symmetric. A second property is that it is also positive. The matrix is also positive. To see that, consider an arbitrary vector A, scalar product with moment of inertia acting on the same vector A. Insert the definition of the moment of inertia. And you see this is sum over nu, m nu, a scalar product with, and then we have r nu prime vector product with a vector product r nu prime. Again, we have this double vector product, which we can write as r nu prime scalar product r nu prime times a minus scalar product r nu prime with a r nu prime. Now this again is, we have to take the scalar product with a, and this gives r nu dot r nu, that's nothing but r nu prime squared, absolute value squared. A dot a gives absolute value a squared. And we subtract from that the scalar product of r nu prime with a squared. Now the absolute value of a scalar product is always less or equal the product of the absolute values. So the second term in the square bracket is always less or equal the first term. So in other words, the square bracket itself is always larger or equal to 0. So the whole thing is, and the masses are also positive, so the whole thing is never negative. It's always larger or equal to 0. And this means, by definition, that theta is also positive. So it's symmetric and positive. This implies, in turn, that theta has non-negative eigenvalues and it can be diagonalized. So theta has non-negative eigenvalues. Let me call these theta 1, theta 2, and theta 3. And There is associated with these eigenvalues are eigenvectors. These eigenvectors form an orthonormal basis. If you normalize them, they form an orthonormal basis. So there's an associated orthonormal eigenbasis. And the basis vectors of this eigenbasis, so these eigenvectors, they span the so-called principal axes of the rigid body. So such an orthonormal eigenbasis of the moment of inertia always exists. And if we want, we can choose that eigenbasis as our body-fixed frame. And it will turn out that this is a particularly useful choice for the body-fixed frame, the eigenbasis of the moment of inertia. Two additional little remarks. First remark, one sometimes talks about the moment of inertia with respect to a particular axis. Here we've introduced the moment of inertia as a linear operator. When one talks about the moment of inertia with respect to a particular axis, and let me denote this axis by a unit vector n, then what is meant is the component of the moment of inertia with respect to this axis. So it's the scalar product of the unit vector n with moment of inertia in the sense of a linear operator acting on that unit vector n. The second remark is about the distribution of mass inside the rigid body. Up to here, to make life and calculations simpler, we assume that the rigid body is composed of n mass points, so we always had discrete sums over all the mass points. Often, however, you don't have discrete mass points, but you have a continuous distribution of mass, and then all the results carry over, only that you have to replace discrete sums over all the mass points. You have to replace these discrete sums by integrals over space, and then you have a density function, that's the mass density, which may vary with position, so it's a function of position, and then the rest. So everything carries over, only that you replace sums by integrals, and you introduce a density. As the last topic of today, let me talk about the kinetic energy of a rigid body. We return now to the picture of discrete mass points, because that's always a bit simpler to work with sums rather than integrals. We have to add up the kinetic energies of all the mass points. So we have 1/2, and then we have to sum over all the mass points, and then we have the kinetic energy of an individual mass point, which is 1/2, and then its mass m nu and its velocity r nu dot squared. We had already seen earlier that the r nu can be related to the r nu primed, the position vector in the body fixed frame. The difference is this distance vector d. When you take the time derivative of that, then you get d dot plus r nu dot, but r nu dot in turn was given by angular velocity vector cross r nu prime. When we use this result, this blue expression for r nu dot, then we can evaluate the square, and then we get three contributions. We get 1/2 total mass of the rigid body. Yeah, so this is sum over nu m nu times d dot squared. Then we have a contribution 1/2 sum over nu m nu, and then we have omega vector product with r nu prime squared. And then we have a mixed term that has the form d dot scalar product with omega cross, and then now if I take the sum inside the bracket, so sum over nu m nu r nu prime. Let's look at the last term first. We have a d dot there. Now in the scenario where the reference point, where we have a top and the reference point coincides with the point that we keep fixed, in that scenario this is equal to 0. Yeah? So if reference point is fixed. In the other scenario, where the reference point coincides with the center of mass, in that case, this sum is equal to 0. This is 0 if the reference point is the center of mass. So whatever scenario we have, this last term vanishes. So we are left with the first two terms. This term here, this is called the kinetic energy of translational motion, and also denoted by T trans for translational. This is because what enters in here is the d dot. The d dot describes how we have a d dot different from 0 only in the case that there's no point is kept fixed, so the rigid body can move freely. In that case, we said the reference point coincides with the center of mass, so the d dot then describes the velocity of the center of mass. And then what we have there is 1/2 times total mass times velocity of the center of mass squared. So it's the kinetic energy associated with the motion of the center of mass. And if the body was a mass point rather than a rigid body with a finite extension, then this would be the only contribution to the kinetic energy. And then we have the second contribution, and that's the one that from now on we would like to focus on, this one here. This is called the kinetic energy of rotation, because this is the only term in which the angular velocity enters. And it describes the kinetic energy associated with the rotation of the rigid body. And this is denoted by T rotational. And this is the energy that we would like to focus on. On the next page, and that's the last page for today, I would like to show you a very simple expression for the rotational kinetic energy. So recall the formula from the previous page for the rotational energy. And let me write out the squared of this bracket as a scalar product. This has the structure of a triple scalar product. Triple scalar product has the structure some vector A scalar product with B vector product with C. Now a triple scalar product has the property that it's invariant under cyclic permutation of the vectors. So A dot B cross C is the same as C dot A cross B, for example. Yeah? It's invariant under cyclic permutation. Doesn't matter whether it's clockwise or anti-clockwise. In particular, it's the case that's of interest here is counterclockwise cyclic permutation. When we use that property of the triple scalar product, then the first vector in the triple scalar product becomes omega. The second vector becomes r nu primed, and the third becomes omega cross r nu primed. We still have in front of that, we have the sum over nu, m nu, 1/2. And then you recognize what I encircled in blue. By definition, this is the moment of inertia acting on omega. And the remaining factor is simply a 1/2 omega scalar product with theta omega. We just learned that the moment of inertia is non-negative, is positive semi-definite. So immediately this implies that the scalar product omega with theta omega is never negative, it's always greater or equal to 0. So as we would expect, the rotational energy of a rigid body is always larger or equal to 0. And this expression here, the simple expression for the rotational energy, 1/2 omega theta omega, looks very similar to the expression for the kinetic energy of a single mass point. There you have 1/2 mass times velocity squared. And you see that there's an analogy here. We have the same structure. It's 1/2 omega theta omega. And there it's 1/2 mass times velocity squared. So there's a formal analogy between mass and moment of inertia and between ordinary velocity and angular velocity. It's of course not a strict analogy, but it's maybe a way that helps to memorize the formula.